Okay, picking up on 4.10, bear with me through some technical difficulties, guys. We have our cosine equation with our phase shift of shifting it forward pi over 2, or if you want to think of it as time, that would be forward 4.5. Let's jump up to number 6, because number 6 asks us, with that equation, can we find out when the rider is 80 feet above the ground? Well, same thing we just did, only now we're setting it equal to 80. So let's go through this. Setting it equal to 80, we want to subtract 50 from both sides. Now we want to divide both sides by that leading coefficient of 40. And now we have the cosine of this complicated pi over 9t minus pi over 2 is equal to 3/4. So just like before, we're taking the inverse cosine of both sides to kind of undo this cosine and ask ourselves, where is the cosine equal to 3/4? Where is the cosine equal to 3/4? Now we can't just go to our unit circle for this. That is not a unit circle value. So this is where it gets kind of tricky. We do have to go to our calculator. So we're just going to input that into our calculator. Inverse cosine of 3/4. Make sure you're in radian mode, and that's what you should get. So remember, these pi over 9 and pi over 2 values are just numbers. So we're going to add pi over 2 to that weird little decimal 0.7227, and then we're going to continue to get t by itself by multiplying by pi over 9, and we end up getting 6.57. 6.57. Let's go back to our wheel really quickly to make sure that makes sense. So here's our wheel. 6.57 is going to be in this neighborhood over here. Well, remember, this is 50, this is 90, so yeah, I think that makes sense. But there's got to be another place where that height off the ground is 80 also. There's got to be another place. So if we found the point right here, just past that highest point of 90, can we kind of work backwards and find the point over here just before? That's what I want you to work on. And see me during office hours. Tell me what answer you get. Let's work through it together. So at this point, pause the video, double check your 4.10 warm-up, double check number 6 that we just did. We're going to skip 5 and 7. If you want to know answers to those, I've got them, but we're going to skip 5 and skip 7. Pause the video, and then when we pick up, it'll be at task 411. Okay, and here we are on task 411. Again, if you want answers to that 410 task, or if you want to check your work, come to office hours. I'd love to look over it with you. But here we are at 411, and we're using another context. Instead of the Ferris wheel, we're going to now look at tides. If you guys didn't know, tides are modeled after sine, cosine, these periodic waves. So if you guys have ever been to the beach, they usually have a board. Sometimes it's a whiteboard. It used to be a chalkboard, and they'll actually draw out a sine curve and show you the high and low tides based upon the sine curve. That's true modeling of how these trig functions are used. Well, you are getting super frustrated of building your sandcastle and having it wiped away by the tide, so you bring your super smart trig friend with you, and together you analyze what you're watching and you come up with this amazing equation right here. F of t, which represents the distance, how far in or out the tide is, equals 20 sine pi over 6t, where t is hours since midnight. Let's just kind of clarify part of this equation first. This 20 is the amplitude. So that's how far out in the ocean the tide is at any point, or how far in towards the beach the tide is at any time. Average tide line is 0, so it can be both positive and negative. Pi over 6. Pi over 6 is our frequency, which controls our period. That's going to say how often the tides go in towards the beach, out towards the ocean, in towards the beach, out towards the ocean, in towards the beach, out towards the ocean. Think about that as controlling how many times in a 24-hour period, in a 12-hour period, how many times a day we're going to see that cycle of high tide, low tide, high tide, low tide. So on number 1, it just wants to know, what is high tide, our largest amplitude? What is low tide, our smallest amplitude? Number 2 then says, we're planning to build our sandcastle right on average tide line, right on 0. How much time will we have to build? So that's referencing our period. So think about that full sine curve. If I build right here on the average tide line, how much time do I actually have to build? On the next page, I want you guys to graph your function. And I've gone ahead and graphed this one for you. It's because this is going to be super valuable in going forward. If you notice, our x-axis is time of day, and it goes by the hour. And our y-axis is height of the tide, or how far out the tide is. And I went by 2 feet. And this gives me a nice scale to be able to use this graph going forward. So on number 4, it says you want to build your sand castle at 10 feet below the average tide line. So if you notice, I actually drew a line right here at 10 feet, so I can visually approximate what time I think that happens at. And just by looking at the graph, it looks like maybe right there around 6.5 hours, and right here closer to 11.5 hours. When I go ahead and solve for those values on number 4, make sure they come back to those values, because that's what we can do. We can actually set our equation equal to -10 and solve. So question number 5 is now saying we want to build it at 15 feet above average tide line. So looking back at my graph, I drew that line right there around 15 feet. And I can, again, estimate, where do I think that point is? Well, to me, it looks about 4.5. Where do I think that point is? Well, it looks kind of like 13.5, which would be like 130. So I'm going to ballpark between 430 and 130. But setting the equation equal, setting it equal to 15 will give us those exact times. And I'm going to go ahead and give you the answer on this one, because I want you to be able to work toward it. The answer is about 9 hours. So my ballpark was pretty close. It's between 4:22 a.m. and 1:37 p.m. See if you can do the algebraic steps to get you from one point to the next. And the last part of this task is asking you, suppose you decide you need only 2 hours to build. You just need a little 2-hour window. Well, look at your graph. How far down into the ocean can you actually build and still give yourself a 2-hour window? I love this task because I think it makes us think really creatively about how to use this sine graph. This sine graph right here can give you just about everything you need, and then we can use the algebraic steps of solving, setting it equal and solving to verify those numbers. So have some fun with this one. Come see me in office hours. We'll be talking about this one on Tuesday. Thanks, guys.